said not? You said not?
Not that one either. Magnetic flux.
So for everything that we did for electric, like electric field, electric charge, all like stuff like that, there is a magnetic analog.
Is there a magnetic charge?
Not all.
So, if they can find a magnetic monopole, then there is a case for a magnetic charge. In which case, the math's already been done.
Yeah.
So theorists have sat down and figured out, if it does exist, here's the math. And they've laid it all out, and so if you looked at Maxwell's equations that, for every electric Maxwell equation, you can just sort of change the subscripts and you've got the magnetic version. It has not been found yet, but when it does, the math is ready.
Yeah.
So other than that, yeah, there's a whole lot of analogs there. So what Maxwell realized is that he could create an electric current from a magnetic field on a different wire. My understanding of the history of it is that he did not actually come up with the math from it, that Lenz, L-E-N-Z, came up with the math. So generally the math equation is called Faraday's law, but I prefer Faraday-Lenz's law. And it tries to express this. So let's see if we can actually formulate, back to answering Jack's question. I've heard it attributed to several physicists. Faraday was the first one I heard it attributed to, but he was basically felt that this was a huge breakthrough in physics, the fact that you could create a current from a changing magnetic flux. And had reporters over, and he was telling them this, and one of the reporters asked, of what use is this? And Faraday's reply was, of what use is a newborn child? So, for a lot of the things that we're doing here, of what use is it? To find out what happens, perhaps it'll lead to something bigger. I mean, it takes, in grad school we figured that for any new math that's discovered, it takes about 500 years before it becomes useful. Physics, about 50 years.
Hey, it's a hell of a senior quote. For what use is a newborn baby?
Yes. All right, so Faraday-Lenz's law. It is saying that, well, if I have a current here, that means I have a potential difference. That potential difference is usually summed up as the EMF. So this is the EMF. It's equal to the negative change in the magnetic flux over time. Now, some textbooks make it seem like what Lenz contributed was the negative sign.
Is that magnetic? Is that a B or an E?
That's a B. Sometimes I'll write an M because that's just the way my mind works sometimes.
So, I'm assuming the calculus for like analog to this would be the d over d of x.
DT.
Or yeah.
D phi dt. D phi sub B dt. Negative. All right, so what does the negative mean? Realize that when this current is created, it creates its own magnetic field. So if this created a current, which created a magnetic field, which then created a current in here, which then created a magnetic field in here, and sorry, I skipped a step there. Create a current, creates a magnetic field, which creates a magnetic flux. That magnetic flux change in here causes a current. That current is going to flow, creating its own magnetic field, and therefore its own magnetic flux over here. If the current created in here creates a magnetic flux change in this one to make the current stronger, it would be a runaway process. If the induced current helps the other current, then this will help that, which helps this, which helps that, and suddenly it blows up. We as a species, I suspect, would be dead by now.
So, by saying that the first one, the circuit with the switch, sort of extends itself to the other one, but not make an entirely new one.
It extends itself to the other one, but the current induced in this is,
Can't reach over back to the.
well, it does reach over, but it's trying to destroy what this was creating. That the negative sign is telling us that the EMF is producing a current which opposes the change in the magnetic flux. So the way I've drawn this is the magnetic flux would be going counterclockwise. So, sorry, the current would be counterclockwise. From this wire right here, this creates a magnetic field. Current's going that way, creates a magnetic field going into the board and out of the board. The wire over here, my current's going this way, so it creates a current that, or a magnetic field like this. And then from that one over there. Because this wire is closer, the into the board is going to be stronger than out of the board. So I have a net magnetic flux coming out. So it goes from 0 to something going that way. So let me make sure I worded that correctly. The current flowing down here, and I'm going to draw this slightly differently. Let's neaten that up. It's not changing anything really. I'm going to add some colors. I make the connection. I have current flowing this way and that way, and that way and that way. So that's my current flow here. The current from this wire flowing down that way creates a magnetic field. Using the right hand rule, the magnetic field from this wire right here is going into the board and out of the board. The magnetic field from the other one, from the other side, it creates a magnetic field going out of the board and into the board. So out of the board and into the board. I have competing magnetic fields here, but because the red wire is closer, the magnetic field going into the board is stronger than the magnetic field coming out of the board. So I have a net magnetic field into the board here. My magnetic flux is increasing in that direction. It goes from, because before I shut the circuit, there was no current at all, there was no magnetic field. So I start out with 0 magnetic flux. When I make the connection, I have a net magnetic flux that way. The induced current says, no, nature does not want a runaway process. Or if it did, again, end of all things. So this runaway process, to avoid the runaway process, this line current induced here has to oppose the change in flux here. Well, I got a change in flux. Didn't actually write the formula for flux, for those who have forgotten. Magnetic flux would be, assuming B is constant. I can change flux by either changing the magnetic field or changing the area. Well, I'm not changing the area, so it comes from changing the magnetic field. My current here will try to oppose the change, my change again, into the board. It's from the magnetic field into the board. It's going to create a current going this way. Because this, and I should have gone for a different color. Ooh. If my current, induced current, is flowing around like that, it creates a magnetic field coming out of the board, inside, which opposes that which is going in.
So, the second, I'm just gonna say circuit, cancels out one of the charges, but it still has some of the, not charges, force from the magnetic field of the first box, but there's still the other direction that's going into it, so it has that left over.
You're talking about the fact that I've got a green and red here going in opposite directions?
I'm talking about the blue ones you just made.
Right.
And
It opposes the net flux here. Since I have an increasing magnet, when I make the circuit, I have an increasing magnetic field going into the board. The blue current there creates a magnetic field that opposes that,
Okay.
so it going out.
And does that equal it out to 0, or does it just lessen?
It lessens.
So that's why it doesn't explode.
Well, if it went in the other direction, then it would explode. Because then it would be adding to it, then I'd have an increasing magnetic field there.
So we don't set it up like it's going that direction, that's just kind of what happens?
Yeah, that's nature saying, I don't want you to die.
How is it going into the board if that current on the, like, the current here is coming here, out of the board?
The magnetic,
Or no, so the current is going this way,
the current is going this way,
and the
counterclockwise.
and the magnetic field is then, oh, the magnetic field is going down, going into the board, okay, I got it.
Okay.
Because for the magnetic field on the top line, it would be going into the board on top and then out.
Yeah,
Okay, got it.
yeah, that's not really gonna have much of an effect over here.
Got it. Makes sense.
All right, here we go.
And is the magnetic field always in the same direction of the current? Or, sorry, we can
The two current. They'll transfer.
we can use the, like, the fact that you're able to draw a red line going down next to the current in the same direction as.
No, that red line is the current.
Oh.
That just highlighted, gave that two-dimensional, the three-dimensional effect, so you could, if you look at it just right, you get depth. That'd be cool if I could actually draw that, but let's pretend.
Yeah.
White or red magnetic field. So I got the uniform magnetic field. I have a loop of wire here that is moving this way. When it enters, so when the wire enters, if we have a change in magnetic flux through this loop. Since I have a change in magnetic flux through the loop, I am inducing a current. In which direction will that induced current go? In this wire right here. And the answer is either clockwise or counterclockwise.
So the magnetic force is coming out of the board or into the board?
The magnetic force is coming out of the board. Magnetic field is coming out of the board.
You said, in which direction is the magnetic field in the loop of wire that's now inside of it?
The question is, what is the direction of the current flow through this wire right here?
Oh,
So,
clockwise.
through the yellow wire, I'm going to induce a current because the magnetic flux is changing inside it.
My thinking is, if the magnetic field is going this way, the current in the coils will kind of continue that and go, I guess that's clockwise.
So they would go that way.
Yeah.
Yes.
Which way, if I have a current that's going clockwise, which way will the magnetic field be in the middle?
Into
Since I'm increasing my magnetic flux here, I need this induced current is going to try to decrease it. It's going to try to decrease it by putting a current so that the magnetic field opposes this increasing magnetic field.
So it doesn't want to go with the magnetic field?
When you say go with the magnetic, no, it wants to create its own magnetic field that is opposite this, opposite of this. So it would be clockwise. Because it creates a magnetic field going into the board.
Oh, okay.
So if I have a current that is going around like that, in this section right here, and I'll pretend I can get a different color here. In that section right there, which way is the current going?
Into the board? Or no, that's different.
It's either up or down.
Yeah. Down?
Yeah, because the current's going clockwise, at that point it's going down. What is the direction of force acting on that segment of wire?
Into the board. Wait.
Hold on. Direction force into the.
We got a current flowing down. The magnetic field is out of the board.
Oh.
Right or left?
Left.
So as this is moving this way, this magnetic field, again, this is all going to the nature doesn't want to run away process. As this comes into the magnetic field here, that the force on this leading wire is going to be opposite the direction of motion. Yes?
Isn't the coil of wire, isn't the magnetic field into the board? Is it like?
Right, but the wire is not exerting a significant magnetic field on itself.
So, what did we decide was the direction of the force?
The direction of the force is that way, on the leading wire.
Okay.
Force is down, the current is
Oh,
down,
left.
magnetic field, the external magnetic field is into the board.
Mhm.
No, sorry, out of the board.
Yeah.
The thumb points that way. So it's being forced back. If it pointed in the same direction, all you have to do is take a loop of wire, get a magnetic field, just sort of give it a nice tap into it, and that thing would just go shooting off again. Think of the weaponization. All physics leads to weapons. If in doubt, that's what you do it for. Weapons.
Shoot particles at people?
Or, big enough magnetic field, or long enough magnetic field, if, assuming runaway processes were possible, you can stick almost anything in there.
And does that tractor mean?
Those maglev trains couldn't stop.
Well,
Let's take it one step further,
let's.
conceptually.
Now, I know we're still on the conceptual part, but is there math involved? Like, is there gonna be something we calculate?
Yeah. I'm coming up to the Princess Bride reference. That involves math. Any of you watch Princess Bride over the break?
I walked in spirit.
All right, I have some sort of surface down there. This is just a side view. Imagine it's a, yay wide superconducting. I take a magnet. And just for the sake of this, we'll have the north side pointing downwards. I know that there are magnetic field lines coming out of a magnet. I have it that goes out of north externally into the south. If I take this magnet and I drop it, the magnetic flux, the magnetic field is going to get stronger the closer the magnet gets to it. As that magnet gets closer to it, magnetic field increases, therefore the magnetic flux increases. It's going to induce a current here, which wants to oppose that. That induced current is basically going to create its own magnetic field that wants to reduce that change, and so we'll induce a current that creates a magnetic field going this way. Well, if I got a magnetic field going that way, I basically created an electromagnet with a north and south pole. I have a north pole and a north pole which will then oppose each other, so that magnet will stop falling and it will move back up. As it moves back up and reaches some sort of whatever the peak is, it will stop moving, the current will go away, and the magnet will start to fall again.
Until it repeats.
And what you have is,
Levitation.
yeah.
So that's how we can figure out like the whole flying cars thing.
All right, so the flying car thing is probably gonna need more. All right, so let's flash back to before you were born. I think that's true for all of you. When I was teaching in Columbia, South Carolina, all I needed to do is have a wire moving through a magnetic field. So if I have a magnetic field going down like this, and I take a wire and I loop it through like that, when the wire is like this, the magnetic flux is zero because the area is perpendicular to the magnetic field.
Right.
As I go around like this, the magnetic flux is increasing because B dot A. Magnetic flux increases, which means I'm inducing a current in the wire.